Okay, we'll begin. Today we are covering Chapter 8. Chapter 8 covers hypothesis testing. Okay? And with hypothesis testing, this is a statistical method for us to answer questions about the population. Based on a sample. Okay. With hypothesis testing, you start off with a claim or a question, okay? Okay, and this claim or question, this is the hypothesis. Okay, start with a claim or a question, and we write it in a way so we can test it. Okay, and then and then you have your data. Okay, and then you ask kind of, what would I expect to see if the hypothesis were true? Okay. Okay, and so we can call this the expectation. And the data will be our reality, I guess. Okay, and then so you would compare the expectation versus the reality, okay? If they are very different, that would give us an indication that our hypothesis is wrong. Okay, and if they are not very different, okay, so if they are similar, if the expectation and reality are similar, okay, then the hypothesis could be true. And so this is kind of a high-level view of how hypothesis testing is going to work. All right, these are kind of the big picture ideas, and we'll try we'll try out a couple examples, and then we'll get into the nitty-gritty of calculating out these hypothesis test things. Okay. Okay. So again, we start off with a claim or a question. We call this the hypothesis, and we write it in a way that we can test it. Okay. And then we have the data that we actually gather. And then we kind of ask, what would we expect to see if this claim or hypothesis were true? And we compare what we actually see versus what we expect to see. If they're quite similar, then our hypothesis could be true. It doesn't prove that it's true, but it says it could be true. On the other hand, if the expectation under the hypothesis is very different from what we actually see, that's a strong indicator that the hypothesis is wrong. Okay, so let's just try a little example out. Okay, so let's say you're playing a game of chance. Okay. Okay, you play a game of chance with, we will call this a friend. Okay, and basically the friend flips a coin. He flips a coin, and if it lands heads, you win. And tails, he wins. Okay. Okay. Scenario 1. Okay, you play 10 games. Okay. And it lands heads 3 times. Okay. And the question we have is our friend cheating when he's flipping the coin, or is he playing fair? Okay. That's what we want to know. Okay. So we're going to put this in such a way that we can test it. We're going to say the claim will be, let's assume our friend is playing fair, meaning the probability of heads is going to be 0.5, right? Our testable hypothesis will be the friend is playing fairly, so that means the probability of heads is equal to 0.5. Okay, is this so far so good with everybody? Mm-hmm. Yeah, okay. Okay, if he's playing fairly, how often do we expect to win? 50% of the time, okay. So the expectation is to win 50% of the time. Okay, and what is the reality? We won 30% of the time. Okay, and we played 10 games. Okay, so what do you think? Do you think this is evidence that the friend is cheating, or could we have just been unlucky? Well, I mean, there's no way to know, but what's your gut feeling here? Huh? So, I would say something like this could happen just from being unlucky. Okay. Okay. Right. Like he could be cheating. We don't know, but.
He wouldn't cheat and get 30%.
Well, I mean, he could be cheating, but I mean, he might be smart about it, and he's cheating in such a way that he's only going to win just a little bit, okay? But if we were to accuse him of cheating, he just says, no, you just got unlucky, and we don't really have an argument against that, right? So I mean, he could be cheating, but it's quite possible to just get these results just from bad luck, right? So I'll write that. He could be cheating. So we haven't proven that he's not cheating. Okay? But at the same time, but I'll just write, but it is quite possible to get these results from simply bad luck. Quote unquote bad luck. Or in other words, just random chance. Okay? Because if I had you all flip coins right now, some of you would get only 3 heads out of 10. Okay? If I all had you flip coin 10 times right now, some of you would only get 3 heads out of 10. Okay? Some of you might even only get 2 heads out of 10. And that could happen quite a bit just from random chance. Okay. So at this point, we don't have any evidence to convince us that he's cheating. Okay? It doesn't prove that he's playing fair, but we don't have any evidence that convinces us that he's cheating. Okay, is this a fair statement? Do we agree with this line of thinking right here? Okay, so let's copy the same thing. Okay, except this time scenario 2. Can I flip to the next slide? Okay. Scenario 2, we're going to play 1,000 games. Okay. Okay. So we play 1,000 games. Okay. And it lands heads 300 times. Okay. And again, we have the same question. Is our friend cheating, or is he playing fair? Okay, so now okay, and so again, our testable hypothesis is the same. Okay, we're going to say friend is playing fair. Playing fairly which means the probability of heads is equal to 0.5, okay? And so our expectation is that we would win 50% of the games, right? Okay, what is the reality that we experienced? Okay, the reality is we won only 0.3 of the games, and we played 1,000 of them. Okay, and so we're asking same question. You know, is the reality different enough from the expectation to convince us that our friend is cheating? So, what do you guys think?
It's the same.
Well, it's 30 to 50. The difference, it's still a 30% to 50% comparison, but this time we've played 1,000 games, okay? And so do you guys feel like the friend is cheating?
Yeah.
Yes or no?
Yes.
Okay, so if we were to accuse the friend of cheating, maybe he says, no, you just got unlucky, okay? And do you think you could have just gotten unlucky? Not that unlucky, right? I mean, it technically it's possible, okay? But we can actually do the math to see exactly how unlucky we have to be for us to win only 300 games out of 1,000, okay? And this is how hypothesis testing works. We say, so we accuse him of cheating, okay? We say, I think you are cheating, my friend. Okay, and then and he says, no. You just got unlucky. Okay. All right, so in order to counter this, we're going to say, okay. So back again, we say, okay. I will give you, for argument's sake, let's say you were playing fairly, okay? Let's assume you are playing fairly. Okay. We can then ask, what is the probability then that a fair coin would land only 300 times out of 1,000 flips, okay? That a fair coin, I'll say lands heads. Only, we'll say 0.3 of the time, or less, out of 1,000 flips. Okay, so we're just basically asking, you know, if we're playing fairly and you're saying this happened by chance, what's the probability that this would happen by chance? That's all we're asking, okay? Because we said, I think you're cheating, and he says, no, you just got unlucky. This just happened by chance. And so we're going to say, okay, well, let's do the math and figure out what the probability that this will happen from chance, okay? Does that line of argument make sense? Okay? And we would expect that this number, because we think he's cheating, we expect that this probability is going to be what? High or low? We expect that this probability is going to be very, very low, right? And that's what's convincing us that he's cheating. Okay? Well, can we answer this question? Sure. Do you want to try? Sure. All right. So let's, I'll copy this. All right. So this is, okay. So this is, I mean, this is why, this is how our progression in statistics has brought us here. Okay. Right. Okay. So we said, you know, how many coin flips do we have? We have 1,000. Okay. And our, we got 300 heads. So our p hat is 0.3. Okay. And if it's a fair coin, then the probability of heads, our p, is actually what? 0.5, okay? And so, sampling distribution, we know that p hat comes from what kind of distribution? A normal distribution. What is the mean of this normal distribution? 0.5, okay. And what's the standard deviation of this normal distribution? No. Square root of p times 1 minus p divided by n, right? So this, we're saying this is the mean and this is the standard deviation, okay? Yeah, this one's p. Yeah, this is p. Okay, and so this, when you plug in all the numbers, you get, you know, you got 0.5 times 1 minus 0.5 divided by 1,000. And you take the square root and you get like a really small number, right? 0.015 or something like that. All right, let's 0.01581. Yeah, okay. Okay, so this is our standard deviation, all right? And then in our picture, we have a normal model. Okay. The mean is centered at 0.5, and we are down at 0.3, okay? And we want to know what's the probability of getting 0.3 or less, okay? All right, what's the z-score then? We would do, yeah, 0.3 minus 0.5 divided by 0.01581, right? Okay, and what does that come out to be? Oops, that's not right. Okay, you're getting a z-score of negative 12.65, is that what we're getting?
Yeah, but isn't the z-score x minus the mean, which would be 300?
It's what we're doing is the reality versus the expectation, right? So the reality is 0.3. This is the proportion we got, 0.3, or the expectation is 0.5. Okay, so we're getting a z-score of negative 12.65. Okay, is that a big z-score? Yeah. It's off the charts, right? It's literally off the charts. So, yeah, because we said, from the empirical rule, we said anything more than 2 standard deviations away is pretty unusual. And we have nearly everything within 3 standard deviations, okay? So anything more than 3 standard deviations is really unusual. And here we are at over 12 and a half standard deviations away from the mean. This is extreme, extreme, extreme. Huh? This would be quite remarkable if it were to happen just from random chance. Let me see. I'm going to use my computer program here to see if it can even give me a number associated to negative 12 and 0.65. Okay, so we're on the order of 6 times 10 to the negative 37. So this is about 6 times 10 to the negative 37. So this is basically, we've got 37 zeros, or 36 zeros, okay? And then a 6, okay? So we got 36. All right, let me just look up what the probability of getting a royal flush on the first deal would be, okay? Or what's the probability of winning Powerball? We'll say Powerball probability. 1, 2, 3, 292. 1 in 292 million. So Powerball is 1 in 292 million. I think this is the equivalent of winning Powerball 2 weeks in a row, okay? Like you buy one ticket and then you hit it, and then you buy one ticket the next week and then you hit it then, okay? So, and that's how unlucky we would have to be. We would have to be unlucky enough for something like that to happen, okay? So is it technically possible? Technically, it's possible. But if that were to happen, if you were to buy one ticket and win Powerball and then come back the next week and then buy a ticket and win Powerball, actually, I think, no, it's like, let me see, 292 million squared. Oh, no, yeah. No, it's I'm sorry. It's on the order of winning Powerball. You buy one ticket and you win it 4 weeks in a row. Okay? So, or can you imagine if the same numbers in Powerball got drawn 4 weeks in a row? People would not say, oh, that was just a lucky chance that the same numbers hit 4 weeks in a row. There would be an investigation. People would say, something is wrong with the system, right? If, let's say, next week the numbers 1, 2, 3, 4, 5, 6, 7 got drawn. And then the following week, 1, 2, 3, 4, 5, 6, 7 got drawn. You know, and it happened 4 weeks in a row. That something we would say this is not quite right, okay? And so, you know, our friend is just saying, no, you just got unlucky. Man, we just happened to draw the same Powerball numbers 4 weeks in a row. No, this would be a strong case that this couldn't happen, okay? So, I mean, technically it is possible, but it is so incredibly unlikely that we say, I don't think it happened by chance. I'm convinced that you are cheating, okay? So, yeah, not our friend anymore. That's why I put him in quotes in the beginning. Okay. So okay, so, you know, technically, these results are theoretically possible. Okay? But it is so incredibly unlikely, but they are so unlikely to happen from random chance. Okay? So this is an indication to us that our hypothesis that he's playing fairly is wrong. We have a question.
Yeah, the z-score, it's like it was x minus, the mean minus x, right? Or x minus the mean. In this case, it's reality minus expectation.
Yeah, yeah. In this case, it's p hat minus p. If you want to get, it's actually p0 is what we call it. But
so in the case of testing hypotheses, you can say it's reality minus expectation.
Yeah, yeah, yeah. Or some books will say observed minus expected, but yeah, pretty much the reality, what we observed, versus the expectation, reality minus expectation, divided by the standard error. Yeah. Okay. Okay. So technically, these, I should say, these results are theoretically possible, but they are so unlikely to happen from random chance. Okay. So we conclude that the assumption of fair play is wrong. Okay. So we have this all down? Okay, so there's a few key terms that, that exist for all hypothesis tests. And so I'll define them here, and then I'll put them in the context of kind of this cheating example that we did. Okay, so we always start off with a pair of hypotheses. Okay, and they always come in two hypotheses together. We have the null hypothesis, which is 0. Okay, and this is kind of like the status quo. There's often written with the quote hope that we get to reject the null hypothesis. Okay, the null hypothesis will always have an equal sign in it. It's an H0. H0. Like null would be 0, right? Okay. And then we have the alternative hypothesis. This is HA, okay? And this is, it's going to be identical to the null hypothesis. Okay, except the equal sign is replaced with either not equal, or a greater than, or less than. Okay. So this would be not equal, greater, or less. Okay, and the choice of not equal greater or less depends on the question asked. Okay, and then we calculate something called a p-value. Okay, so the p-value, this is the probability of observing our data or something more extreme if the null hypothesis were true. I'll say were assumed to be true. Okay, so this is these are three kind of key things that you'll need to know. All right, so let's we'll star this page. Okay, and let's we'll go take a look at the cheating example and identify what the null hypothesis, alternative hypothesis, and p-value would be in these cases. Yeah, question.
Yeah, what is that word? Is that the choice? The choice of
The choice, yeah, the choice of not equal, greater than, or less than.
what do you mean depends on the
Depends on the question asked. What do I mean by that?
yeah, like the choice of it.
The choice.
In the question it's given. You'll see that in the question.
Yeah, no, okay, so the question is going to be asked, so we've only seen one example so far, okay, but I hope maybe as we see more examples it'll make more sense. But the question will ask something like, you know, is this evidence of something, 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 okay? And the way that question is written will determine whether your alternative hypothesis should use the not equal sign, greater than, or less than sign, okay? Which will have an impact on how we calculate the rest of the steps, okay? Okay, so if we go back to, you know, our question is our friend cheating? Okay, so what we have is the hypotheses. We have our null hypothesis, which is our friend is playing fairly. Okay. And the alternative is our friend is cheating, and specifically is cheating in a way to give us a disadvantage. Okay. Okay, so this is our hypotheses written out in words. We can we're going to turn these symbolically, and this is where we have the equal sign and whatnot. Okay, so the thing that is of interest to us is what's the proportion that we would win? Okay, so P would be kind of the proportion that we win. Okay, and it's the proportion that we win kind of in the population. So it's not just the data that we see, but it's is the system set up in such a way that the proportion we win kind of in the long run, is that set up in such a way to give us a disadvantage, okay? So our null hypothesis would say our friend is playing fairly. The proportion that we would win kind of in the long run or in the population is 0.5, okay? That's what we would expect if the coin is flipped fairly, right? The alternative, what would our alternative be? Okay, so the alternative is always identical to the null hypothesis. Everything is exactly the same, except we replace the equal sign with either a not equal, a greater than, or a less than. Okay? So we're going to have P is going to be the same, and 0.5 is going to be the same. And the alternative is our friend is cheating to give us a disadvantage, right? And the P is being the proportion that we win, so we would expect this to be less than 0.5, okay?
So how would you, since it's 0.5, don't you just say it's not equal since it is half? Since 0.5 is half, it's not 0.5, don't you just say it's not equal?
I'm sorry.
The probability is 0.5, right?
P is 0.5. That's what we would expect if the game is being played fairly, yes.
So that's 50%.
Correct.
So if it's not 50%, won't you just say it's not equal since it's 50?
That it's
Asking about the symbols,
It's
like,
simple, yeah.
that it's not equal to 50%?
Why would you just write not equal?
Yeah, because here, I guess because we're selfish or whatever, we would not question if our friend is cheating if we happen to win more than 50% of the time, right? Like, because it doesn't make sense for, like, if the friend's going to be cheating, it doesn't make sense for him to give us an advantage, right? So if we end up winning 55% of the games or more than 50% of the game, we would not question, oh, are you cheating? Like, that doesn't make sense, right? So here the only instance that makes sense to us is if we're winning less than what we expect, okay? And so it's either he's not cheating, we're playing fairly, or we're winning less than what we expect. Yeah.
Does it matter that on the left side you phrased it as our friend is cheating to give us a disadvantage as opposed to our friend is cheating to give himself an advantage?
Okay, if we want to say our friend is cheating to give himself an advantage, okay, it really comes down to what does P define, okay? If P is the proportion that we win, it makes sense that we were going to check P is less than 0.5, okay? If we're going to say our friend is cheating to give himself an advantage, it would probably make sense to rephrase P to be the proportion that our friend wins, and in that case, P would be greater than 0.5, okay? So it kind of depends on what you define P to be, okay? And so P is kind of the proportion that we win, and giving us a disadvantage or giving himself an advantage would mean that the proportion we win is less than 0.5. Okay? All right, is this okay in setting up our hypotheses? Okay? All right, so our p-value in this situation is the probability of observing our data or something more extreme, if the null hypothesis were true. Okay, so in the context of this problem, our data is 1,000 games, and we win 30%. So it is, it is the probability that a fair coin lands heads %30 or less out of 1,000 flips. Okay, that is the p-value. Okay, so here I just kind of want to say, observing our data, the probability of observing our data is the coin lands heads 0.3. Okay, or something more extreme is the or less. Okay, so the reason why we have to bother with this 30% or less is because if we were going to accuse our friend of cheating because we won only 30% of the games, we would also accuse him of cheating if we won 29% of the games, or if we won only 28% of the games. So it makes sense to include all of the times we would accuse him of cheating, which is winning 30% or anything less. Okay, 30% or less. And then this part where if the null hypothesis were true, okay, this part comes in where it says a fair coin. Okay. All right, and we did the math here, okay, and then the math from a few slides ago said that our z ends up being negative 12.65, and the probability, the p-value associated with that, is on the order of 6 times 10 to the negative 36 or 37 or something like that. 37, I think. Okay, just something very extreme. Yes?
So why is your alternative hypothesis not p is less than or equal to 0.3?
Yeah, because I guess I just have to kind of defer back and say we're testing to see if it's either fair or if we're being disadvantaged, okay? We're not actually interested, we're not calling into the question, is the coin rigged in such a way to give us 0.3? We're actually only interested to see if the coin is doing something to be less than 0.5. This is we happen to get 0.3, but we're not actually interested if it's exactly 0.3 or not. We just want to know, is it less than what it's supposed to be?
But would we question it if it was like 0.48?
We could question it, and what we would probably find is that when we find the probability associated with getting 0.48 or less, the p-value there is fairly large. Okay, and we can explain all of this. Okay, so but for this the previous example, these would be our null hypotheses and our alternative hypothesis, and then the p-value is the probability of getting our data. Okay, and what we found was because our p-value is so small, we come to the conclusion that the null hypothesis is wrong and that the alternative hypothesis is true. Okay? Okay. Is that good? All right, why don't we take a short break here, 10 minutes, and then and we'll come back and continue.